Hi guys, we're going to finish up with 2007. Before we do that, I want to go back and clear up something that I messed up with on the last problem. On the last problem, it was a KSP problem, and we had AG3PO4, and that broke up into 3AG plus PO4 minus, and we had ice, 0, 0, ended up with 3x and x. So in this case, KSP was going to be equal to 3x to the third multiplied by x. So that equals 9x to the fourth in that case. Just wanted to clear that up. For some of you that might have been confused on that. Okay, so what we're going to do next is we're going to move on to 2007 Form B. It's the last one we're going to do. And this problem was the first one that we actually did as a class, and it gives us a bunch of stuff. And really, I'm just going to really work through this by doing the ice chart first, and going from there. So we have a reaction U3O8 solid plus 3Cl2 gas goes to 3UO2 gas plus O2 gas, blah, blah. And here we go. Let's start trying to fill it in. A sample of U3O8 is placed in a rigid 1.5 liter flask. Chlorine gas is added, and the flask is heated to 862 degrees Celsius. First thing we want to recognize is this doesn't count. It also says chlorine gas is added, but it does not tell us how much chlorine gas is added. So we have a question mark for chlorine gas. It also tells us that it was added to a rigid flask, but nothing else was in it. So that was 0. I can go ahead now and say minus 3x. I can say plus 3x, and I can say x. I can say question mark minus 3x. I can say 3x, and I can say x in this case. Okay, moving on. It gives us the Kp expression, and because it's Kp, we're looking for atmospheres. When the system is at equilibrium, the partial pressure of Cl2 is 1.007. So they gave us this. That's great. That's this. Okay, and we know it's there because they said at equilibrium. And the pressure of UO2Cl2, which is actually this, sorry, that's equal to 9.734 times 10 to the negative fourth. Okay, so this is 9.734 times 10 to the negative fourth. Well, we're then going to know that the pressure of O2 is basically using stoichiometry or using common sense. We know that's going to be that value divided, this value divided by 3, and that's going to end up being 3.245 times 10 to the negative fourth. Okay, so we got our values. Let's move on and let's see how much of this problem we can solve, given the information that I have. Calculate the partial pressure of O2 at equilibrium. Let's go back. I think we did that. Yep. There's the answer to A. The partial pressure of O2 at equilibrium is X. So C, ice chart. B, calculate the value of the equilibrium constant Kp for the system at equilibrium. Okay, Kp is going to be equal to UO2Cl2 raised to the third power multiplied by O2 divided by Cl2. Now I know that they're putting like these P's in front here. All they're doing is denoting that we're talking about partial pressure here in terms of Kp. So we're going to plug in the values that we got, 9.7 times 10 to the negative fourth, multiplied by 3.245 times 10 to the negative fourth. This is raised to the third power, and they're dividing that by 1.007 to the third, and we're getting 2.9 .31 times 10 to the negative 13th. Great, moving on. C, calculate Gibbs free energy. So delta G equals delta H minus T delta S, delta G equals negative NFE, and delta G equals negative RT ln of K. You can get this from the equation sheet. We're going to be using this one because we're talking about K in this case. So we're going to plug it in. We're going to use the value of negative 8.31 for R. Our temperature in Kelvin is going to be 862 plus 273, and that's because they give that to you in degrees Celsius. And we're going to take the natural log of our K value, which was 2.31 times 10 to the negative 13. That was this value that we saw for in that previous problem. And you're going to plug it all in, and you're going to get a value of 272 kilojoules per mole. Now, before we move on, let's talk about what this means. This means delta G is greater than 0. It means it is non-spontaneous. It's always a good idea to stop back and reflect on what your numbers mean. Alright, D. State whether the change of entropy, delta S, is positive, negative, or 0. Well, if you look back at the reaction, you have 3 moles going to 4 moles, and you also produce gas, so this reaction gets messy. So we know that delta S is going to be greater than 0, increasing entropy. Well, it looks like what they're doing is they're walking us into a God, I hate this stuff equation. So far we've had the delta G is positive, so far we've had the delta S is negative. Let's see what's coming next. State whether the delta H for the reaction at 862 is positive, negative, or 0. Well, the only thing we can do is relate the variables that we've already solved for. We know that delta G was positive. We don't know delta H. We know that delta S was positive. Restating this in a more easy format, I could have this. Now, the only way for delta G to end up being positive is if this is positive. So delta H must be positive to satisfy the delta G equals delta H minus T delta S equation. I'm going to read you the actual answer that they have, the College Board produced. They said, both delta G and delta S are positive and determinant in parts C and D. Thus, delta H must be positive because delta H is the sum of 2 positive terms in the equation. So, basically, delta H must be positive to satisfy this equation. That's essentially what they're saying. Let's move on to the next one. So, after a certain time, 1 mole of O2 is added to the mixture in the flask. Does the mass of U3O8 in the flask increase, decrease, or remain the same? Well, if you look back to the reaction, you're increasing O2, which is on the product side, so it's going to shift to reactants. So we're going to have a left shift, okay, but no change because U3O8 is a solid, doesn't count. Alright guys, take care. Look forward to seeing you in class.